Night settles softly, like a quiet tide washing over the edges of the world. The noise of the day fades into a distant memory, and all that remains is the gentle rhythm of your breath and the vast, silent sky stretching far beyond what the eye can see. Above you, the stars seem still, almost eternal, as if they have always been there and always will be. And somewhere among those distant lights, there is one that matters more than most. A faint glow, barely distinguishable unless you know where to look. It is called Alpha Centauri, our closest stellar neighbor, quietly waiting just beyond the edge of our familiar cosmic home. If you enjoy drifting into these calm, reflective journeys through the universe, you can gently support the channel by subscribing or following along. It's a small gesture, but like a distant star, it helps keep this quiet exploration glowing. Now, as your thoughts begin to slow, let a simple question settle into your mind. It's a question humanity has carried for generations, whispered under countless night skies. Are there planets orbiting those nearby stars? And if there are, could any of them hold life? To understand that question, we first need to gently approach the system itself. Alpha Centauri is not a single star, but a small family, 3 stars bound together by gravity, moving in a slow, ancient dance that has lasted for billions of years. At its heart are 2 stars, Alpha Centauri A and Alpha Centauri B. They orbit each other in what astronomers call a binary system. Imagine 2 suns circling a shared center, never drifting apart, yet never colliding, locked in a delicate gravitational balance. Alpha Centauri A is the larger of the 2. In many ways, it is strikingly similar to our own sun. Its color, its warmth, even its brightness feel familiar, as though it could light a sky much like the one we know. If you stood on a planet orbiting it, the sunlight might feel almost like home. Its companion, Alpha Centauri B, is slightly smaller and cooler, glowing with a softer, more orange hue. Together, they complete a full orbit around each other roughly every 80 years. Sometimes they draw closer, about the distance between the Sun and Saturn. At other times they drift farther apart, stretching the distance to something closer to Pluto's orbit. This slow, graceful motion creates a complex gravitational environment, one that shapes everything around it. And then, much farther away, there is a third member of the family, Proxima Centauri. Smaller, dimmer, and glowing faintly red, Proxima orbits the central pair from a vast distance. It takes hundreds of thousands of years to complete a single journey around them, like a distant companion quietly circling from afar. Despite its size, Proxima Centauri has become one of the most intriguing stars in the sky, not because of how it shines, but because of what may orbit it. Within this system, we have already discovered at least one planet, Proxima b. It is roughly the size of Earth and orbits close enough to its star that, in theory, conditions might allow liquid water to exist. This places it within what scientists call the habitable zone, a region where temperatures are neither too hot nor too cold. But the story is not so simple. Proxima Centauri is a volatile star. It flares violently, releasing bursts of radiation that could strip away an atmosphere and bathe the surface of any nearby planet in harsh energy. A world there might be constantly exposed, its skies unstable, its surface shaped by forces far more extreme than anything on Earth. And yet, the possibility remains. Because Alpha Centauri is not just another distant system, it is the closest one to us, only about 4 light years away. In the scale of the universe, that distance is almost intimate. It makes Alpha Centauri more than just a point of light. It makes it a destination. For decades, scientists have wondered whether planets could even form in such a system. The gravitational pull between Alpha Centauri A and B creates a dynamic environment where stability is not guaranteed. Some theories suggested that any forming planets might be torn apart or flung into deep space. But newer research and advancing technology has begun to challenge that assumption. There may be planets there after all, perhaps even more than one. Around Alpha Centauri A, astronomers have detected hints, subtle signals that suggest something might be orbiting the star. A faint point of light, seen briefly, then gone. Not yet confirmed, not yet understood, but enough to keep the question alive. If such a planet exists, it could be unlike anything we have yet studied up close. Perhaps a gas giant, similar to Saturn, moving through the system on a wide elliptical path. Or perhaps something smaller, hidden deeper within the glare of the star, waiting to be revealed. And this is what makes Alpha Centauri so compelling. It is not just nearby, it is familiar. The stars themselves resemble our Sun more closely than most others we have studied. That similarity raises a quiet, persistent hope that somewhere in that system there could be a world not entirely unlike our own. A place with skies and oceans, with clouds drifting across a warm horizon, with the right balance of light and distance to allow life not just to exist, but to evolve. We do not yet know if such a world is real, but for the first time in human history, we are beginning to look closely enough to find out. And as you lie there, letting your thoughts drift further into the quiet, you can imagine it, a distant planet circling a familiar sun, its light traveling across space for years before finally reaching us. A small signal, hidden in the glow of a star, carrying with it the possibility of something more. Perhaps one day we will know. Perhaps one day Alpha Centauri will no longer be just a distant neighbor, but the first step toward understanding whether we are alone. Until then, it remains where it has always been, waiting in the silence, just beyond the edge of our sky. As your thoughts continue to drift through that quiet expanse, something subtle begins to emerge beneath the wonder, a difficulty that has followed astronomers for generations. Finding a distant world is not simply a matter of looking harder. It is, in many ways, a problem of light itself, because the stars, as beautiful as they appear from Earth, are overwhelmingly bright, and the planets that orbit them are not. Imagine for a moment that you are trying to observe a tiny object in the distance, not in darkness, but in full daylight, with a powerful light source shining directly into your eyes. This is the challenge astronomers face when searching for worlds around stars like Alpha Centauri A. A star emits an enormous amount of light, billions of times brighter than any planet that might orbit it. That light floods the surrounding space, washing out everything nearby. Even the most advanced telescopes, for a long time, could see only the star itself. Anything smaller, dimmer, more subtle, simply disappeared in the glare. A planet, even one as large as Jupiter, reflects only a tiny fraction of that light. It does not shine on its own. It borrows brightness from its star, and in doing so, becomes almost invisible against it. Astronomers often describe this challenge with a simple but striking image, trying to see a firefly hovering beside a lighthouse. The lighthouse beam sweeps across the horizon, powerful and unrelenting. The firefly flickers softly, its light delicate and easily lost. From far away, no matter how carefully you look, the brightness of the lighthouse overwhelms everything else. The firefly is still there, but hidden. This is what it means to search for an exoplanet near a bright star. Not just distant, not just small, but nearly erased by the very light that reveals its existence. And yet, despite this, humanity has not stopped looking. Instead, we have learned to change the way we see. This is where a new kind of instrument enters the story, one that does not simply observe the universe, but carefully filters it, reshaping the light itself so that hidden things can emerge. High above Earth, far beyond the distortion of the atmosphere, the James Webb Space Telescope drifts in a stable orbit, quietly unfolding one of the most ambitious engineering achievements ever created. At first glance, it does not resemble a traditional telescope. Its most striking feature is its mirror, large, segmented, and coated in a thin layer of gold. These golden panels are not decorative. They are designed with precision, optimized to collect a specific kind of light, infrared. Unlike visible light, which our eyes can see, infrared light carries information about heat. Warm objects, even those that do not shine brightly, emit it naturally. And this changes everything, because while a planet may be dim in visible light, it can glow faintly in infrared, revealing its presence in a way that was once impossible to detect. The Webb telescope does not just look, it listens to the quiet warmth of the universe. But even with this advantage, the problem of brightness remains. The star still dominates the scene, flooding the telescope with light that can obscure anything nearby. So astronomers needed another solution, something more precise, more deliberate. They created a tool that behaves almost like an artificial eclipse. It is called a coronagraph. Inside Webb's instruments, including the highly sensitive MIRI, the coronagraph works by blocking out the light from a star. Not completely, but enough to dramatically reduce its intensity. It is as if you were to hold your hand up to the sky, shielding your eyes from the sun just enough to glimpse something faint beside it. But this is not a simple act of covering. The coronagraph must operate with extraordinary precision. Light behaves like a wave, bending and scattering as it passes through space and around objects. Even the smallest imperfections can create patterns, rings, spikes, subtle distortions that might be mistaken for real celestial bodies. So the system is carefully engineered to control not just the brightness of the star, but the structure of its light. Some coronagraphs physically block the center of the image. Others manipulate the phase of incoming light, causing it to cancel itself out through interference, like waves in water meeting and flattening into calm. The result is a dramatic increase in contrast. Where once there was only a blinding point of light, now there is space, darkened, quiet, and filled with possibility. And within that space, something faint might begin to appear. A small glow, a subtle presence, a planet, perhaps, slowly orbiting just beyond the edge of visibility. This is how Webb changes the game. It does not make planets brighter. It makes stars quieter. And in that silence, the universe begins to reveal what it has been hiding. The combination of infrared observation and coronagraphic masking creates a new way of seeing. Instead of relying only on indirect signals, tiny wobbles in a star's motion or slight dips in brightness, astronomers can now attempt something far more direct. They can try to capture the light of the planet itself. Not perfectly, not clearly, at least not yet, but enough to suggest form, position, movement. Enough to begin asking more detailed questions. What is its temperature? How far does it orbit from its star? Could it hold an atmosphere? These questions, once purely theoretical, are slowly becoming measurable. And all of this unfolds in the quiet darkness of space, far from the noise of Earth, where the Webb telescope continues its patient work. It does not rush. It does not announce discoveries with certainty. Instead, it gathers data, light, faint and ancient, traveling across years of empty space before finally reaching its mirror. Each photon carries a story. Each observation adds a small piece to a much larger puzzle. And as you rest there, letting your mind follow this slow and careful process, you can begin to sense the scale of what is happening. Not just a search for planets, but a refinement of perception itself. A shift from blindness to awareness, from glare to clarity. Somewhere near Alpha Centauri, hidden in the brightness of familiar stars, there may be worlds we have not yet truly seen. But now, for the first time, we are beginning to create the conditions where seeing them is possible. Not by overpowering the light, but by learning how to gently move it aside. As the silence deepens and the distant machinery of observation continues its patient work, something remarkable begins to take shape. Not just theory, not just possibility, but actual discoveries. Small, fragile signals pulled from the overwhelming brightness of nearby stars, hinting that these distant systems are not empty after all. Among them, one stands out more clearly than the rest. Orbiting the faint red glow of Proxima Centauri is a world known as Proxima Centauri b. It is, in many ways, the closest thing we have found to a neighboring Earth. Not identical, not confirmed to be alive, but close enough to stir something deeper than curiosity. Proxima b is roughly similar in size to our own planet. Not a giant, not a gas world, but something solid, something that could, at least in principle, have a surface. It orbits its star very closely, completing a full journey in just 11.2 Earth days. By our standards, that distance is incredibly small. It lies far closer to its star than Mercury does to the Sun. And yet, because Proxima Centauri is so dim, this tight orbit places the planet within what astronomers call the habitable zone, the region where temperatures might allow liquid water to exist. Water, the simplest requirement and perhaps the most essential. A place where it is not frozen into ice forever, nor boiled away into nothingness. A narrow balance, delicate and rare, where chemistry can become something more. But even here, the story is not simple. Because Proxima Centauri is not a calm star, it is restless, unstable, prone to sudden and violent flares. Bursts of radiation surge outward, sometimes thousands of times stronger than anything our Sun produces. And Proxima b, so close to its star, would be directly exposed to these events. Its skies, if it has skies, may be constantly disturbed. Its surface, if it has one, may endure a relentless storm of energy. There is also the quiet but profound effect of gravity. At such a close distance, Proxima b is almost certainly tidally locked. One side of the planet always faces the star, bathed in endless daylight. The other remains in permanent night, a frozen hemisphere where the sun never rises. A world divided in two. On one side, heat. On the other, cold. And yet, between them, there may be a narrow region, a twilight zone where day meets night, where conditions are more stable, a place where temperatures soften, where the extremes balance just enough to allow something gentle to persist. If life exists there, it might exist in that quiet boundary. But Proxima b is not alone. Astronomers have identified at least one smaller companion, Proxima Centauri d, a much lighter world orbiting even closer to the star. Its year lasts only a few days, and its conditions are likely far too extreme for life as we understand it. There are also hints, uncertain, debated, of another object, sometimes referred to as Proxima c. Its existence is not yet confirmed. The signals that suggest it may be there could just as easily be noise, artifacts of measurement, or the subtle complexities of the star itself. And so, even in our nearest system, certainty remains elusive. But perhaps the most intriguing mystery lies not around Proxima, but around its brighter sibling, Alpha Centauri A. In 2024, using the extraordinary capabilities of the James Webb Space Telescope, astronomers detected something unusual. A faint point of light, barely visible, but consistent enough to stand out against the noise. They called it S1. It was dim, about 10,000 times fainter than the star itself, but clearly present. Positioned at a distance that could correspond to a planetary orbit, it immediately raised a question. Had we finally glimpsed a planet around a sun-like star in the nearest system to Earth? But then, something unexpected happened. When astronomers returned to observe the same region in 2025, the object was gone. No trace, no signal. Only the familiar patterns of scattered light and instrumental noise. At first, this disappearance might seem like a mistake, evidence that the original detection was flawed. But the explanation may be more subtle and more fascinating. If S1 is a planet, it may follow an elliptical orbit, one that carries it closer to the star at times and farther away at others. When it moves too close, it could slip into the region blocked by the telescope's coronagraph, hidden once again in the star's overwhelming glow. Or it may pass behind the star entirely, vanishing from view. In this sense, the disappearance is not proof of absence, but a clue about motion. A hint that something may be there, moving through space in a slow, predictable path, occasionally stepping into visibility before retreating again into light. And so the discoveries lead naturally into a deeper question, not just whether these worlds exist, but whether they could truly be places where life might take hold. The idea of habitability begins with a few simple requirements. Liquid water is one of them. Temperature is another. But these are only the beginning. A planet must also hold on to its atmosphere. It must be protected, at least partially, from radiation. It must maintain stability over long periods of time, millions, even billions of years, for life to emerge and evolve. For Proxima Centauri b, these conditions are uncertain at best. The intense radiation from its star could strip away its atmosphere, molecule by molecule, over time. Without a strong magnetic field, something that may be weakened by its slow, tidally locked rotation, the planet would be exposed, its protective layers gradually eroded into space. There is also the possibility that early in its history, the planet lost much of its water. When Proxima Centauri was younger, it was brighter and more active. Any oceans that may have existed could have evaporated, their hydrogen escaping into space, leaving behind a dry, barren world. And yet, even here, there are possibilities that remain open. If Proxima b has a thick atmosphere, rich in gases like carbon dioxide, it could redistribute heat from its day side to its night side, smoothing out the extremes. Instead of a planet split into fire and ice, it might become a world of shifting winds and balanced climates. There is also the idea that the planet may not have always been so close. It could have formed farther away, where conditions were gentler and only later migrated inward. In doing so, it might have avoided the most destructive phase of its star's early life. Another possibility is more subtle. Early in its history, the planet may have been surrounded by a thick envelope of hydrogen, a temporary shield that absorbed the worst of the star's radiation. Over time, that hydrogen could have escaped, leaving behind a more stable, secondary atmosphere beneath it. In each scenario, the outcome is different. A dead world, a harsh world, or perhaps a world that still holds on to the fragile conditions needed for life. As you drift deeper into rest, these possibilities remain suspended, uncertain, unresolved, but quietly compelling. Not answers, but directions. Not conclusions, but beginnings. Somewhere in the dim red light of Proxima Centauri, or in the golden glow of Alpha Centauri A, there may be worlds we are only just beginning to understand. Worlds shaped by forces both familiar and strange. Worlds that may, in their own quiet way, be asking the same question we are. Waiting, in the darkness between stars, to be seen. As the night deepens and your thoughts drift further into that quiet expanse, the search itself begins to feel less like a distant scientific effort and more like a slow, careful listening. Because finding a world across the vast darkness is not a single act, it is a collection of subtle techniques, each one designed to notice what cannot be seen directly. Long before telescopes like the James Webb Space Telescope could attempt to capture the faint glow of distant planets, astronomers relied on something more indirect. They learned to watch the stars themselves, searching for the smallest signs that something unseen might be pulling on them. One of the earliest and most reliable methods is called the radial velocity technique. Imagine a star not as a fixed point, but as something that gently moves, almost imperceptibly, under the gravitational influence of an orbiting planet. As the planet circles, it pulls on the star, causing it to wobble slightly back and forth. This motion is incredibly small, but it leaves a detectable signature in the star's light. When the star moves toward us, its light shifts slightly toward blue. When it moves away, the light shifts toward red. By measuring these tiny changes with extreme precision, astronomers can infer the presence of a planet, estimate its mass, and even determine the shape of its orbit. This is how Proxima Centauri b was first discovered, not by seeing it, but by sensing its quiet gravitational influence on Proxima Centauri. Another method feels almost poetic in its simplicity. It is called the transit method. If a planet's orbit happens to align just right with our line of sight, it will pass directly in front of its star, blocking a tiny fraction of the starlight. For a brief moment, the brightness of the star dips, so slightly that it might go unnoticed without precise instruments. But if this dimming repeats at regular intervals, it reveals something extraordinary. A planet passing between us and its star again and again, marking time with its orbit. From these transits, astronomers can measure the planet's size, its orbital period, and sometimes even detect the composition of its atmosphere as starlight filters through it. And then there is the most challenging method of all, direct imaging. This is the approach made possible by technologies like coronagraphs and infrared observation. Instead of inferring a planet's presence, astronomers attempt to see it directly, capturing its faint light against the overwhelming brightness of its star. It is here that instruments aboard Webb, including MIRI, begin to play their most delicate role, creating just enough darkness around a star to allow something hidden to emerge. But each of these methods carries its own limitations. Radial velocity can detect the pull of a planet, but it struggles with smaller worlds, especially those far from their stars. The signals become faint, buried in noise. The transit method depends entirely on alignment. If the orbit is tilted even slightly, the planet will never pass in front of the star from our perspective, and we may never know it is there. Direct imaging, though powerful, is still constrained by distance and brightness. Only the largest and brightest planets, usually far from their stars, can be detected this way with current technology. And so, the search continues as a combination of all three, each method filling in the gaps left by the others, slowly building a more complete picture of distant systems like Alpha Centauri. Within that picture, the mysterious object known as S1 begins to take on a more defined shape, not as a confirmed world, but as a possibility shaped by physics and inference. If S1 is real, its characteristics can be roughly estimated from what little we know. Its brightness suggests that it may not be a small rocky planet but something larger, perhaps a gas giant, comparable in scale to Saturn. A world of swirling clouds and deep atmospheres, reflecting just enough light to be seen across the vast distance. Its orbit, if the observations are interpreted correctly, may lie somewhere between 1 and 2 astronomical units from Alpha Centauri A, a distance not unlike the region between Earth and Mars in our own solar system. At that range, the temperatures might be moderate, depending on the planet's atmosphere and reflective properties. But as a gas giant, it would not have a solid surface where life as we know it could take hold. And yet, its presence could still be deeply significant. Because large planets do not exist in isolation, their gravity shapes everything around them. In some cases, they can destabilize smaller worlds, pulling them out of orbit or preventing them from forming in the first place. A massive planet moving through a system can act like a cosmic disruptor, scattering debris and altering trajectories over millions of years. If S1 follows an elongated elliptical orbit, this effect could be even more pronounced, sweeping through different regions of the system, influencing whatever lies in its path. But there is another possibility, one that shifts the perspective entirely. Gas giants can host moons, and those moons, under the right conditions, could be worlds of their own. In our solar system, moons like Europa and Enceladus already hint at the potential for subsurface oceans hidden beneath layers of ice. If a similar system exists around a gas giant in Alpha Centauri, it is not impossible to imagine a moon with the right balance of heat, atmosphere, and chemistry to support life. In this way, even a planet that cannot host life directly might still create the conditions for life to emerge nearby. A world orbiting a world. A smaller sphere of possibility carried along through space. As your thoughts continue to slow, the focus begins to shift once again, not just to what we have found, but to what we are preparing to find. Because the tools we have today are only the beginning. In the coming years, new observatories will extend our reach even further. Among them is the Nancy Grace Roman Space Telescope, designed to survey the sky with extraordinary precision. It will carry advanced coronagraphs capable of directly imaging planets that are currently beyond our grasp. On Earth, a new generation of extremely large telescopes is being constructed, massive structures with mirrors spanning tens of meters, capable of collecting unprecedented amounts of light. These instruments will push the limits of resolution and sensitivity, allowing astronomers to study distant systems in greater detail than ever before. But perhaps the most transformative advancement lies not in detecting planets, but in analyzing them. Through a technique known as spectroscopy, scientists can examine the light that passes through or reflects off a planet's atmosphere. By breaking that light into its component wavelengths, they can identify the chemical signatures of gases present in the air. Oxygen, methane, water vapor, carbon dioxide. Each molecule leaves a distinct imprint, a pattern in the light that reveals its presence. And when certain combinations of these gases appear together, especially in ways that are difficult to explain through non-biological processes, they may point towards something extraordinary. A biosignature, not proof of life, not yet, but evidence that something is happening, something active, something dynamic. A signal that a distant world is not just a silent sphere of rock or gas, but a place where chemistry has crossed a threshold into something more complex. And so, as you rest in the quiet, the search unfolds not as a single discovery, but as a gradual awakening. From detecting the faint pull of unseen planets, to watching the brief dimming of distant stars, to capturing the fragile glow of worlds hidden in light, and finally, to reading the atmospheres of those worlds, searching for the subtle fingerprints of life itself. Somewhere within Alpha Centauri, these methods may one day converge. A planet detected, a signal confirmed, an atmosphere analyzed, and within it perhaps the first true hint that we are not alone. Until then, the instruments continue their quiet work, and the stars remain as they have always been, steady, distant, and filled with possibilities waiting to be understood. As the quiet deepens and the distant worlds you've imagined begin to settle gently into the background of your thoughts, the story moves beyond observation. Because at some point, simply watching is no longer enough. The question changes. Not just what is out there, but could we ever go there? For all the sophistication of telescopes like the James Webb Space Telescope, they remain observers, patient, distant, and still. But there is another kind of ambition quietly forming within human imagination, an ambition not just to see, but to reach. And this is where the idea of interstellar exploration begins. Among the most compelling concepts is a project known as Breakthrough Starshot. It does not rely on massive spacecraft or traditional propulsion. Instead, it proposes something far more delicate and far more radical. Tiny probes, no larger than a chip, each one attached to an ultra-thin reflective sail. From Earth, an array of powerful lasers would fire into space, focusing their energy onto that sail. Light itself, photons, would transfer momentum, pushing the probe forward faster and faster until it reached a significant fraction of the speed of light, up to 20% of it. At that speed, the distance to Alpha Centauri, more than 4 light-years, could be crossed in just a few decades, not centuries, not millennia, a human lifetime. It is a quiet but profound shift in perspective. For the first time, Alpha Centauri is not just a distant point of curiosity. It becomes a reachable destination, a place we might one day send something real. something built by us, something that could pass through that system, capturing images, measuring atmospheres, perhaps even glimpsing the surfaces of worlds like Proxima Centauri b as it flies by in silence. But like all ideas that stretch the limits of possibility, this one carries immense challenges. The first is material. A sail pushed by laser light must be incredibly light, yet strong enough to withstand intense radiation and acceleration. It must remain stable, not tearing or deforming as it is driven forward by a concentrated beam of energy. Even tiny imperfections could cause it to spin, drift, or fail entirely. Then there is the question of energy. To accelerate even a gram-scale probe to such extraordinary speeds would require an immense amount of power, far beyond what we typically use for space missions. The laser array itself would need to be vast, precise, and sustained, focusing its output across thousands of kilometers without losing coherence. And finally, there is the challenge of miniaturization. Everything the probe carries, its camera, its sensors, its communication systems, must be reduced to an almost unimaginable scale. It must survive the journey, endure impacts with interstellar dust, and still function when it reaches its destination. And once it does, it must transmit its data back across light years of space, sending a signal so faint that it may take years to arrive. Each of these challenges is formidable, but none of them are impossible. And that is what makes the idea so quietly powerful. As your thoughts drift through these possibilities, the focus begins to soften again, expanding outward into something broader, something less technical, but perhaps more important. Because beyond the engineering, beyond the physics, this entire search carries a deeper significance. Scientifically, every discovery adds to our understanding of how planets form, how systems evolve, and how common or rare the conditions for life might be. By studying systems like Alpha Centauri, we begin to see patterns. We learn whether Earth is typical or unusual, whether life emerges easily given the right conditions, or whether it is the result of an extraordinarily unlikely sequence of events. Each new planet detected, each atmosphere analyzed, contributes a small piece to that larger question. What is the probability of life in the universe, not in theory, but in reality? And yet, alongside that scientific inquiry, there is another layer, quieter, more reflective, a philosophical layer. For as long as humans have looked at the stars, we have wondered not just about what is out there, but about ourselves, our place, our significance, our solitude. Are we alone? It is a simple question, but it carries enormous weight. If the answer is yes, if life exists elsewhere, even in its simplest form, then the universe is not silent. It is alive in ways we are only beginning to understand. Life would not be unique to Earth, but part of a larger cosmic process, unfolding across countless worlds. But if the answer is no, if, after all this searching, we find nothing but empty planets and lifeless systems, then something else becomes clear. That what exists here, on this small, fragile planet, is rare. Perhaps unimaginably rare. A brief and delicate emergence of complexity in an otherwise quiet universe. And in that case, the responsibility changes. Because if we are alone, then we are not just observers of life, we are its only known expression. A single point of awareness in a vast, silent expanse. As you settle deeper into stillness, these ideas begin to soften again, dissolving into the quiet from which they came. Because for now, there is no final answer, no confirmed second Earth, no definitive signal of life beyond our world, only hints, possibilities, questions that remain open. The search continues, patient, methodical, and ongoing. New instruments will come online, new data will be gathered, new worlds will be discovered, some stranger than we can imagine, others perhaps more familiar than we expect. And through it all, one destination remains at the center of that quiet pursuit. Alpha Centauri, the nearest system, the most accessible, the place where, if life exists beyond Earth, we may find our first true evidence, or where we may confirm, at last, that we are alone. Until that moment comes, Alpha Centauri remains what it has always been, a distant light in the night sky, steady and silent, holding its secrets just beyond our reach. And as you drift gently toward sleep, it is still there, waiting, not with answers, but with the quiet promise that the search itself is only just beginning.